Thank you very much for having the opportunity to present this topic here. I will start with the question about the thermal dose, then coming to the nice abbreviations like PED and so on. So then I will say a few words about thermal dose concepts and modeling, and coming to conclusions and outlook in two parts. When you look to pharmacology, it's clear a dose is an amount of drug administered to the patient. In radiation therapy, it's the absorbed dose per mass, so it's quite different, it's a density. When you go to hypothermia, it would be very natural to see temperature as initial physical quantity, but temperature definitively is not a dose. It's not a quantity, it's an intensity. Here we can see an animal patient, this is a leg from a dog with a sarcoma, and on the left you can see the specific absorption rate distribution, so a sort of dose rate or a sort of power rate distribution. When you look to the right image, you can see the temperature, and the temperature is influenced by the physical distribution of the SAR values, but it's influenced by the perfusion as well. So physiological processes are influencing the dose distribution. That are measurements from bladder patient. Temperature measure in the bladder, here illustrated by the blue curve. The red one is measured in the rectum. And if you look to the upper images, you can see the temperature course during treatment time for the same patient, but two different treatments. When you convert that to a cumulative equivalent minute factor, this factor is telling about the contribution to the cumulative equivalent minutes at a certain time point. You can see that the time course of this CEM factor is completely different for two fractions in the same patient. So we have a physiological and pathophysiological modification of what we reach as temperature in the patient. So how we can compare treatments, how we can introduce dosimetric concept. One idea is that when we look to the synergistic effect of radiation and heat, we can use descriptors for the biological effects, here denoted by lambda and gamma. These quantities are considered as transient biological dose equivalents, and I will say more about the definition of these quantities later. The point is that when we look to the synergistic effect of radiation and heat, we have a combination of two different effects, and the total effect is a sort of overlapping, or is produced by the overlapping of the two effects. For the synergistic effects, then we have a time gap between radiation and heat due to clinical workflow. We have order of application, we have temperature variation during the treatment. We do not know actually what the relevance of all these things is, but there is an important question: how to compare treatment when we look to the complexity of such a combined treatment. Why we want to compare treatment? It would be a nice thing to have a sort of biological treatment planning. For treatment planning, we need patient imaging, we need data preparation and segmentation, then we can get out an electromagnetic simulation model, a thermal simulation model, or a radiation dose model. But when we want to have a biological treatment planning, then we need thermal enhancement data. For that, we propose the concept of the transient biological dose equivalent to describe the biological effect. For treatment planning, we would like to have handy concepts to compare treatment. For that, I will present the concept from the AMC people from Amsterdam, the equivalent dose. So I will focusing on these two things in the whole landscape of treatment planning. There are these nice abbreviations, so I will explain now these abbreviations, coming first to the biological equivalent dose. The assumption behind is the linear quadratic model, and what you can do is comparing the biological effect. By the linear quadratic model, we compare survival. So for the logarithm of survival, we can assume the linear quadratic relationship, and when we go to the low dose rate and low dose limit, so the dose per fraction becomes smaller and smaller, then the quadratic term of the dose can be neglected. So then you get a linear relationship containing the radiosensitivity parameter alpha. Then you have times the dose per fraction and times the number of fraction, and this can be considered as the biological equivalent dose in the low dose rate limit. So BED in the low dose rate limit can be calculated according this. Now you can compare that to another fractionation scheme. So you can go to another dose per fraction, and assuming that you want to have the same biological effect. So in this case, you have to take the linear quadratic law, and you will end up in the well-known formula, which is often used for calculating the biological equivalent dose. The problem behind is that you have to assume linear quadratic behavior. You can look to kinetic or dynamic models like the LPL model from Curtis or even the gamma LQ model, and all these dynamic models show a behavior which is resulting in survival curves which are between the high dose rate limit given by the linear quadratic law and the low dose rate limit which is characterized by the linear relationship of the linear quadratic law. So all these models show a dose rate dependency which is producing survival curves between. But the problem is to determine the alpha values. There are big uncertainties first. Second, from a radiobiological and radiobiophysical viewpoint, it's not clear that here the dotted line is the low dose rate limit. It can be another. So there are big uncertainties, and it's very dangerous to use a biological equivalent dose concept far away from the well-investigated and well-known conditions. For example, when we look to the repair, we can consider repair by adding an H factor, and for two fractions and first order kinetics, this H factor is decaying in an exponential manner. So we can include repair, we can try to include repopulation, but as soon as we include such effects, it's not straightforward to use the formalism proposed by the biological equivalent dose equivalent. It's much more elegant and much more flexible to use kinetic models, and I will show that later using the MHR model. What's the difference to the equivalent dose? The equivalent dose is not comparing a treatment to the low dose rate limit, but it's comparing to a dose per fraction of 2 grays. So we compare a 2 gray fractionation with an arbitrary different fractionation scheme. Even here we assume linear quadratic model and assume that the biological effect between two different treatment schedules should be the same. In this case, you can solve this equation, and you will get the formula or equation to calculate the equivalent dose, so a dose which is compared to a fractionation scheme of 2 grays. Then you can do some cosmetics, so you can divide the denominator and the numerator here of the fraction by the radiosensitivity coefficient beta, and you get an expression where you have the alpha beta ratio in, where you have the dose per fraction for the compared fractionation schemes to the reference dose in. What is outside of the linear quadratic model? Linear quadratic model in principle is only a data descriptive model. It's not really a biophysical model. It's nice to describe survival data. The idea behind is that we have the linear low dose rate limit and that the quadratic term is bending down the curve to this nice linear quadratic shape. As soon as we have dose rate dependency, we have to correct that with the generalized Lee catch site dose protection factor or with another factor which can be multiplied to the beta term of the linear quadratic law. But the problem is that this idea or this is a difficult thing. And I have always the impression, as soon as you go to low dose hypersensitivity and all these complex behavior, you need this nice guy to bend the curve into the right shape. Looking from the radiobiology, I would propose another view to the whole story. I would propose that we have a high dose rate limit, which can be assumed as more or less linear, and induced repair then is bending up the curve to the right shape. A model following this concept is the multi-hit repair model, but I have to point out here that as long as you are looking to survival curves, you will not see the full story. You have not the insight into the full dynamics of the system. It's like a movie, and like looking the last picture on the last picture of a movie, you never will get the story, you never will understand the story. Survival is a biological endpoint, and therefore it's only a part of the systemic behavior of tumor cells. A full dynamic model, which is introducing a concept for radiobiological repair, so it's in principle a radiobiological inspired model, is the multi-hit repair model. And this model has very interesting behavior. We can explain in principle all the radiobiological observations starting by cell cycle dependence, apoptotic versus non-apoptotic cell death, dose rate dependency, or even low dose hypersensitivity can be explained by the same model. And at my knowledge, it's the only model which is covering all these things by the same mathematical structure. But this is radiation. What is for hypothermia? Van Leuven and colleagues from the AMC from Amsterdam introduced a very nice concept, taking the equivalent dose concept. And the idea is that in principle we can assume in the linear quadratic law, we can assume alpha and beta as function of temperature and time interval or time gap between heating and radiation. For alpha and beta, they proposed a nice model which allows to interpolate between an alpha and beta value without heating at 37 degrees and an alpha and beta value determined by, for example, in vitro experiments at 41 degrees, and for the decay of the thermal effect, for example, by repair, an exponential term with the time interval is added at the end. As soon as you have such a model for alpha and beta values, you can bring that to the concept of the equivalent dose concept. So you have to substitute the alphas and betas by this function of temperature and the time interval. Here we have not the comparison of two Gray fractions with an arbitrary other fractionation scheme. Here we have the comparison between a radiation therapy without heat and a combined hypothermia radiation therapy. So it's converting, in principle, the dose to this situation. There is an assumption made. If we assume complete repair between the fraction and no repair during the fraction, the leakage site dose protection factor, which is multiplied here, becomes 1 over the number of fractions, so the total dose divided by the number of fraction, then is the reference dose per fraction, and this is the reason why we have not the total dose here, but this reference dose per fraction. This concept can be extended to direct cytotoxicity, to additive cell killing. The idea is that you have a contribution in the log of survival here, a contribution from the direct cytotoxicity. And the idea is that you can assume a sort of linear kinetics of cell killing. So the cell killing rate is assumed to be directly proportional to a rate constant k, which is a function of the temperature, and the number of cells, for example, of tumor cells. So when you integrate this equation, you will end up in this typically exponential behavior. So the logarithm of survival for direct cytotoxicity is then minus this k factor times the treatment time. In this model, you can bring in some thermodynamics by using the inactivation entropy and the inactivation enthalpy. And when you fix the treatment time, then this product will become a pre-exponential factor, which is a function of temperature, times an exponential function containing the inactivation entropy, inactivation enthalpy, and the temperature. And with that, you can go into the EQD concept, and you have a nice handy concept for calculating the EQD, including direct cytotoxicity. This is a nice thing as soon as you have data. For example, the Amsterdam people investigated a lot of cell lines in vitro, and this is a very nice publication giving an insight into different aspects of those heat and time gap dependence. There is a clear advantage of this method. We are using a more or less established framework. We can look to in vitro data and try to get out the alpha beta values for different temperature. We can try via tumor control probability model to compare that to clinical data. The problem is, as soon as you have nonlinear kinetic, nonlinear dynamics, as soon as you look to the ecosystem dynamic, which could play a very important role in the patient, it becomes difficult to bring that in this concept. In principle, you have to determine alpha and beta values for every situation when you change fractionation schemes, heating schemes, when you change the treatment time, you have to validate that and to measure that by in vitro experiments. And, important point, as long as we look to the survival, it does not tell the story again. So, this leads to the modeling, and there are two aims for modeling. One type of aim is the weather forecast. When you do treatment planning as clinician, you are interested to have a weather forecast. So you are interested to have a prediction for the patient. That are predictive models. Models can be used for a completely different aim. Models can be used for understanding dynamics in a system. As soon as we use dynamic models, we can try to identify characteristic dynamic patterns in silico, in the model, but as well as in the biological data. And this will lead to model-based data analysis, and this I will show or demonstrate by the multi-hit repair model. Modeling a biological system is related to the scales in the biological system. So for hypothermia, it's not clear on which scale we can model or we should model. We have the molecular model, and we can try to model immunohistochemical systems and then comparing that to, for example, in vitro experiments. We can go a scale up, a step up to the fragments of DNA fragments. So then, for example, we can try to look to a comet assay, and we can try to model the comet assay by a model. Or we can go up to the emergent cell reaction, to a more aggregated level of the behavior of the cell. Then we are looking, for example, to survival data in vitro, and we have models which are describing survival in silico. So we can compare that. The multi-hit repair model is able to cover at least two different scales, the biological system. The model itself contains a chain of population. We have undamaged tumor cells N and N, that are the cells undergoing mitosis. And then we have a chain of population, L1, 2, 3, and so on. And this chain of population is describing or are describing cells having a certain amount of severe radiation-induced hits. Severity is defined here implicitly by the fact that as soon as a cell has a severe hit, this cell cannot undergo mitosis. This is implicitly the definition of that. The hit rate is assumed to be proportional to a radiosensitivity coefficient alpha. This is not the same coefficient as used for the linear quadratic law. It's assumed to be linear proportional to the dose rate R. And in this model, in principle, we can add direct heat-induced cytotoxicity by a second outflow. This is not actually done because we restricted our research consequently to a temperature range below 43 degrees. So we focused only on the synergistic effect of heat and radiation. The synergistic effect of heat and radiation is covered by a repair rate. The repair rate is proportional to a repair probability P. And this repair probability P is linked via a statistic model, in this case a Poissonian model, to transient biological dose equivalents for heat and for radiation. So the gamma quantity here is the transient biological dose equivalent for radiation. The lambda quantity is the transient biological dose equivalent for heat. What is the idea behind this concept? I came back to the dose concept. In pharmacology, you have a dose, an amount of drug. You have a kinetic model, which is describing the distribution of a drug in the patient. And then you may have a pharmacodynamical model, which is converting a plasma concentration or a concentration in the target compartment to a biological effect. In radiation therapy, it looks different. You have monitor units as a treatment machine output. Then you have a physical model which allows to calculate an organ dose, and you may have a radiobiological model which converts an organ dose into a biological effect. At first glance, hypothermia looks quite similar. You have, when you heat with radio frequency, you have an RF power output. You will produce a specific absorption rate pattern in the patient, but now you have physiological regulation mechanisms such as perfusion, and this will lead to a certain temperature, and this will lead to a dynamic effect in the tissue. The idea of the transient biological dose equivalent now is that we try to cover the biological effect by a dynamic state variable first. This is the transient biological dose equivalent, and this dynamic state variable is related, should be related to the physical primary quantities like dose and temperature. So we need a biological and a biophysical model. We have to keep in mind that as soon as you are heating with electromagnetic power, there may be there are certainly non-thermal effects. They are not covered by this concept at the moment, so there is an additional thing that we should keep in mind. In the multi-heat repair model, these two transient biological dose equivalents are intended to describe the repair capacity or repair inhibition of the biological system. So on this axis, on the y-axis, you have in principle the strength of inhibition, and as soon as you heat, the lambda dose goes up and describe repair inhibition, and when you irradiate, the gamma dose goes up and describe the radiation-induced inhibition of repair enzymes. The decay after radiation or the decay after heating then is nothing else than the repair of the repair enzymes by chaperones. For radiation, the kinetic model, there is a kinetic model which assumes that the transient biological dose equivalent is rising up with the dose rate R and decaying with the function describing the repair of the proteins. The transient biological dose equivalent is calibrated to the absorbed dose, to the total absorbed dose. When we integrate over the repair function, then we get out the total dose, and this is the reason why this quantity is calibrated to gray. When we look to 3 different radiobiological situations, a situation green with complete repair between the fraction, a situation red with incomplete repair between the fraction, and a situation black with strong incomplete repair between the fractions. So here you can see every fraction, and you can see how this gamma dose is going up and down. From the kinetic model, you can calculate the gamma dose, and with that you can calculate the number of surviving cells. Here the gamma LQ model is taken, but you can do the same with the multi-hit repair model. From that we get the number of surviving cells, and using and with that we can calculate the tumor control probability, and we can convert in principle these situations to tumor control probability. And this shows very nicely how the transient biological dose concept can be used for TCP calculation, not only for first order repair kinetics. We can include here second order repair kinetics, binary exponential repair kinetics. We can introduce here arbitrary repair kinetics. So the concept is very flexible. For the thermal dose, we use an Arrhenius-like approach. So we assume that we have the lambda quantity, which is produced here by this dose rate constant or rate constant K1. And in K1, we have the inactivation energy of the proteins. Then we have, this is the Boltzmann constant, and this is the temperature. So this is an Arrhenius approach. Inactivation energy of enzymes, there are some literature values. It's important to keep in mind that this model does not include additive cell killing. This is only to describe the synergistic effect. So here we measured the thermal dose, or we determined the thermal dose for bladder patients. That are real clinical treatments, the blue dots. And we can see that when we calculate the cumulative equivalent minutes, and when we compare that to the maximum of the lambda dose reached during thermal or during heatment, then we see that we have a good agreement between the 2 concepts. And this is not a wonder. This is simply due to the fact that both concepts are based on an Arrhenius concept. But what we can see as well is that at a certain point of heating, when you heat long or when you heat at higher temperature, you go with the lambda concept, you came into a saturation. And this is not corresponding to what we observe clinically. And the reason is simple, that above 43 degrees, we have other processes taking place, such as direct cell killing, such as other conformal changes on the repair proteins, which are related to other activation energies. So here we see only a small part of the whole story. It's the synergistic effect between radiation and heat. When we look to the time gap between heating and radiation, it's clear that this transient biological dose equivalent fade away due to chaperone repair, and then due to different time gaps which are related to the different patients due to clinical workflow reasons, we get a wide spread of different thermal dose. However, this part of effect can explain in vitro data, for example, here the old data of Separator and co-workers, when we heat here and when we irradiate before, during or after heating, the multi-hit repair model is able to reproduce the data. However, we got the impression by analyzing this data, we got the impression that the whole story can be explained better by 2 processes. One process which is not so sensitive to time gap, and the second process which is more sensitive to time gap. But this is purely hypothetic. At the moment, we have not enough data to really distinguish between these 2 processes. We started to look to Comet assay, and not only to survival. So in a comet assay, you can determine the DNA in the comet tail, which is proportional to the DNA damage that we actually have in the cell. And when we irradiate and heat here and wait a certain time, we can observe in a comet assay how the DNA fragments are disappearing. And so we have an impression how fast and how efficient the cell do repair the DNA damage. So we have taken some comets from a sarcoma, and we fitted here the median values of the comet by the MHR model. And interestingly, when we do that, we can find a parameter set which is able to predict the survival. And this is very interesting. So actually, I would like to make some publicity for Matthias Weiland. He has a talk even on this Congress. What he's trying and what he tried is to assign comets to the population in the multi-hit repair model. We are assuming that a certain number of severe radiation-induced hits are related to a certain amount of DNA damage which can be observed in the comet. And in principle, he took this comet and he tried to map this on the population which are becoming then a histogram bin. This allows us to produce histograms. This is the measured histogram. We have here on the y-axis the tail intensity, which is directly proportional to the DNA damage. We have here the time after treatment, and the width of these violin plots is showing how many cells we have with a certain amount of damage. And these are the in vitro data, real biological data, and this is the synthetic comet assay. And we have now the opportunity to compare a synthetic comet assay, which is predicted from the model, with the biological data. And by comparing the distributions, we get much more insight into the full dynamics of the system. And I would, if you want to learn more about that, Matthias Weiland has his talk tomorrow afternoon in the session 3. So coming back to modeling, thermal dose concepts, and treatment planning. Thermal enhancement data can be analyzed by the MHR model, by model-based data analysis, for example, comparing synthetic comet assay with biological comet assay. This can be used to calculate survival curves. These survival curves can be fitted with the linear quadratic models to find alpha and beta values, and these alpha and beta values can be fed into a therapeutic enhancement model, like the EQD model. This can be used for treatment planning, and this can be used for optimization of the treatment. Again, the transient biological dose equivalent is aimed to describe the dynamics in the system. For treatment planning, we need a handy concept which allows us to compare treatments. This could be done, for example, by the EQD model from the Amsterdam group. I came to the first conclusions. I have 2 sections of conclusions. First, when we look to thermal dosimetry concepts, we should look to time and heating rate dependence in future. We have actually indication that the initial heating rate will strongly modify the biological answer. And if this is the case, we have to look for additional biological processes or mechanisms. So with the combined comet and survival analysis, we will do that in the next time. Comet does not distinguish between the different repair pathway. When we look to non-homologous enjoining and homologous recombination, we need specific marker for that. We proposed a model which could be used for analysis, but in future we should look more carefully on that. But this is the molecular level. We are going down then. We can go up to the next higher scale, to the cellular level, or to the immune system interaction, or to ecosystem dynamics. And it's in a real patient, it's not clear if the game is playing there and not there. Models for treatment planning should be handy concepts. they can be fitting functions in the sense of data descriptive models, but such model will never be fully predictive. To support this model, we need more understanding, and we propose strongly model-based data analysis that we can have a better insight into what hypothermia is really doing. Coming back to the CEM and lambda dose, completely independent of what kind of dose you are using, please have a look to these patients and to these fractions. When we look clinically to real patients, human patients, and we have done the same for animal patients, we find a lot of patients having very, very low doses during the treatment. And we have success. So the question is, when we have a lot of fractions with low thermal doses, and when we combine a few fractions of the radiation therapy course with hypothermia, what the hell is doing the effect? Synergistic effect? What? Oxygenation, maybe? We investigated that by a physiological model, and we found that the effect of the oxygenation mostly is small for one fraction. And when you apply 3 or 5 fractions with hypothermia and you have 32 fractions of radiotherapy, okay, maybe not the main contribution. But if that is not the main contribution, which other process could it be? So coming back to the levels in the biological system, you have the molecular level, cellular level, you have the emergent cell reaction, but above we have another level. We have the tumor ecosystem. We have the patient as dynamic system. And even on this level, you can compare in silico model, a computer model, with data. In vitro, it's difficult. In vivo, it's better. In patient, it's the best, but it's difficult. Actually, we developed a coupled tumor ecosystem model, including the immune system. And we modeled the immune system activation by the tumor and by radiation therapy. So we added a radiobiological model for the tumor cells. We added a radiobiological model for the immune systems present in the compartment. And this is a complete artificial system, I have to say that. This is a sandbox play at the moment, not more. But it's very interesting what this artificial system is showing. For example, when we compare different fractionation schemes, daily fractionation versus a mixed protocol, where the first 3 fractions have a spacing of 2 days between the fraction, we can observe that this mixed protocol is better than the others. And this for a large range of investigated parameters, for a very large range, we find in every case the same. The reason is the reason lies in the population dynamics of the system. When you have a larger spacing at the first fraction, you have more immune system activation, and with the larger spacing, you give the immune system more time to react. So this could be a very interesting concept for combining with hypothermia. When we assume that hypothermia may activate or trigger the immune system, we should give the immune system enough time to react. So I came to the conclusions too. For the clinicians and for the more practical people, the big question is how to perform thermal dosimetry. So my advices are measure, monitor temperature, time resolved, please. Measure, monitor, control specific absorption rate or other parameters which are important for applying hypothermia. Measure time gaps between heating and radiation. And if possible, acquire during the treatment patient-related data, for example, perfusion. This is very, very difficult, I know. But it will help to compare clinical trial. And as soon as we will know more, and we know not a lot, sorry, basic research is still ongoing, but as soon as we will know more, we will come back and inform you about that. And with these final remarks, I will thank to you for the attendance, and I will thank to the team and collaborating partners. There are a lot of people working on different topics here, so this is that are some of the peoples. If there are some questions from the audience, I think we have enough time having a discussion. Thank you very much.
What do you think, what is enough time for the immune system to respond?
This is depending on, yeah, thank you. This is a very important question, and I cannot answer completely. We investigated different speed of invasion of immune cells, and there's an uncertainty. And depending on that, it can be 2 days, 3 days, maybe 1 day is on the limit. We do not know, actually. It would be wonderful if we could look in clinical treatments how fast immune cells invade into the tumor compartment, so how fast macrophages come in, how fast T cells coming in. We investigated different conditions of an immune system, and we found that 2 days may be sufficient, but this information is very unsafe, really unsafe, because a validation is completely missing at the moment. So it's only an idea, it's only an inspiration in which direction we could think at the moment. It would be wonderful to find some people from immunology which are interested to dig in here. I think that we have a lot of patient-specific variability. And this is another important point when you look to immune system dynamics. We have patients having different immune capacity. So this will be a big issue to look in detail for this, and it's not easy at the moment. So here at the moment I'm presenting really a sandbox play, only giving some inspiration in which direction we could think. For example, when we have daily fractionation, 5 days per week, why not combining the hypothermic fractions every Friday? Then we have the weekend, and then we have more spacing. So it's a little bit this direction that I would push on the thinking.
Thank you. You talked about using equivalent dose and biological equivalent dose for the treatment planning. Is that the same as CEM43? The equivalent dose. The equivalent dose does compare a treatment without heating with a treatment with heating. CEM43 is only looking to the thermal effect. Radiation is not considered there. But behind all these dose concepts, we use an Arrhenius-like approach. And depending on activation energy, and for inactivation of cells, direct cytotoxicity, we have inactivation entropy, depending on the parameters, these concepts can be in a certain agreement. But CEM43 does not look to the dynamics of the system. The lambda dose, which is in agreement just to a certain point with the CEM43, is a full dynamic view onto the system. This is the difference. CEM43 is a fixed quantity. The lambda quantity gives the full dynamics of the system. So we should be using lambda?
Yes. If we have the parameters, and we are now fitting different cell lines and looking how the what are the parameter values that we get out. So we have preliminary values for the parameters, but there is an uncertainty simply due to the fact that we analyzed a few cell lines. And we hope that by looking onto Comet assay, we can find better values, and this may help to establish the lambda concept, which is complex concept, or it could help to find alpha and beta values, temperature dependent, which can be used for more handy models such as the EQD model proposed by the AMC.
An experiment on dogs, if I remember. The first group was with local hyperthermia. The second group was local plus systemic hyperthermia, whole body. And the SEM33 in the group, or in the combination group, was 10 times higher than in local hyperthermia group. But clinical effect will be the same, was the same, and toxicity in the combination group was much higher. So what is the value of SEM33?
Yeah, that's a difficult thing. There are big questions behind that, and one point is how the temperature are measured, how thermometry is made, what are the exact conditions of the treatment, but yeah, I do not know. To be honest, I do not know. We see a lot of results which are tricky to find an interpretation of that, but it shows us clearly that more than one effect contributes in a patient to the whole story. And with the most concepts that we had in past, we are always looking to a very specific aspect. So the AMC model, for example, is a model which has both synergistic effect and direct cytotoxicity, but we have not the systemic effect. So we are looking only to a part of the whole story. And when you look to the clinical outcome, you look to the full story, but not to the details. You cannot distinguish between the details, but you see the full story.
This is the same what you were saying. What the hell are doing? What is happening? Low doses, thermal doses, and high effect.
Yeah, I would propose do research. But I'm researcher, not clinician, so it's easy for me to say we need more research, so it's a political statement. Yeah. Okay.